Here in 11.5, we're going to be exploring alternating series, and we'll come up with a test for determining whether an alternating series is convergent or divergent. So first, what is an alternating series? So a series whose terms are alternating between positive and negative. So for instance, 1 minus 1/2 plus 1/3 minus 1/4 plus 1/4, 1/5 minus 1/6, and so on. Right, so this is an alternating series. So here's one way you could express the sum. This factor -1 to the n minus 1 ensures that when n equals an odd value, for instance, when n equals 1, it's a positive value to start with. And then the even index terms will have a negative sign, so they'll be subtracted. Or here's another example where it starts with minus 1/2 plus 2/3 minus 3/4 plus 4/5 minus 5/6, and so on. Similarly, here we have -1 to the n, which gives it the alternating part. So that's one thing you can look out for. If it contains that factor of -1 to the n minus 1 or -1 to the n in the series, you know that it's going to be an alternating series. So what conditions are required for us to determine whether an alternating series is convergent or divergent? So it's actually a very simple test here. So as long as we have an alternating series, in this case b1 minus b2 plus b3 minus b4, and so on. Here all the bn's are positive, but the terms themselves are alternating in sign in the integral, or in the series, determined by this -1 to the n minus 1 factor. So as long as it satisfies these two conditions where bn plus 1 is less than or equal to bn for all n, in other words, another way of saying that is that it's a decreasing sequence, or maybe more specifically it's a non-increasing sequence. So as long as it's decreasing and the limit as n goes to infinity of bn is equal to 0. So you just need those two conditions, that the terms of the series are decreasing and go to 0 in this case. That's enough to guarantee that the alternating series is convergent. Notice that these two conditions would not be sufficient for showing a series is convergent when it's not an alternating series. So this is specific to an alternating series, and we'll see why here if we think about the partial sums of an alternating series. Like here I can imagine here the partial sums are being graphed here on a number line. So for instance, the first partial sum would just be S1. So that would be just B1. Okay. And then I subtract B2, so I'm going to go to the left B2, and that's going to give me S2. So we know S2 here would be B1 minus B2. And then notice that B2 is smaller than B1, so it doesn't go all the way past 0. So here notice that B2 is smaller. And then B3 is again smaller in absolute value, so it's not going all the way past B where B1 was. So S3 would be up here. And then minus B4, now this is going to go, again, it's smaller than B3, so it's going to go not as far as S2. And then each subsequent term is getting smaller and smaller than the previous one. And they're alternating, so they're closing in on some value that's in between each of them. So as this sequence progresses, these partial sums here are going to be closing in on some value here in the middle. So our S is going to land somewhere in between these partial sums. And since the partial sum kind of bounces back and forth from one term to the next, we know that the actual sum of the series must be some value in between them. So that's a good way to picture why we know it only requires those two conditions. One, that the terms of the sequence are getting smaller from one term to the next, and that they eventually go to 0. And otherwise, if they don't eventually go to 0, then they'll just bounce back and forth without getting closer and closer to one value. So here they need to get closer to 0 in order to converge on some value here in the middle. So let's just try it out here with that simple example that we started with, the alternating harmonic series. Remember, the harmonic series is 1 plus 1/2 plus 1/3 plus 1/4, but here the alternating harmonic series is just going to be alternating terms. 1 minus 1/2 plus 1/3 minus 1/4, and so on. And notice that this one's pretty easy to check those two conditions. Right? We can easily see here that 1 over n plus 1 is less than 1 over n. So we have that first condition that bn is less than, or sorry, bn plus 1 is less than bn. So that shows it's decreasing. So there's the first condition satisfied. And then the second condition is that when I take the limit as n goes to infinity of 1 over n, in this case we get 0. Yeah, so notice that here I didn't consider the negative 1 to the n when I'm testing those two conditions, because remember those two conditions that we're testing ignores the alternating sign. It just looks at the terms in absolute value. So with those two conditions satisfied, right, it's decreasing and the limit goes to 0. Therefore, it's convergent by alternating series test. What about this series? The series negative 1 to the n, 3n over 4n minus 1. Clearly it's alternating because it has this negative 1 to the n factor. But does it converge? Well, I can kind of tell just from observation here, 3n over 4n minus 1 does not go to 0. So right there I can see that perhaps that second condition of the alternating series test is not satisfied. So if I take the limit as n goes to infinity of just 3n over 4n minus 1, and in this case, what would I get? So I divide the n. Notice here I get 3 over 4, because here 1 over n goes to 0. So this limit is 3 over 4. So right there I can tell that because this limit is not equal to 0, that this series is not going to converge. In fact, that's one of the conditions that we need for any series to converge, regardless of if it's alternating or not, is that it needs the limit of the terms have to go to 0. Otherwise, if they don't go to 0, then we can say that the series is divergent by the divergence test. So here, since when I take the limit now as n goes to infinity of the alternating series, or the terms with the alternating factor, well, because it doesn't go to 0, this limit doesn't exist. If we can imagine, the terms are getting closer and closer to 3 over 4, so some of them are getting closer to positive 3 over 4, some of them are getting closer to negative 3 over 4. So as the series progresses, you imagine they're getting closer and closer to positive 3 over 4 from one side, but other side they're getting closer to negative 3 over 4. But again, they're kind of bouncing back and forth here. Positive, negative, positive, negative, positive, negative, and so on. They're just getting farther and farther apart as the sequence progresses. So that's why here we say that limit doesn't exist. And since the limit as n goes to infinity here is not equal to 0 in particular, means it's divergent by the divergence test. Remember, the test for divergence just requires us to check that as n goes to infinity, that the terms of the series go to 0. If they don't go to 0, then we can say right away that the series is divergent. Let's try one more example here. We want to test the series -1 to the n plus 1, n squared over n cubed plus 1. So clearly this one is alternating. And now if I want to test to see if this series is convergent or divergent, we'll apply those two conditions of the alternating series test. First condition is to show that it's decreasing. Now in this case it's perhaps harder to make the inequality argument, so what I'll do is I'll use a derivative instead. If I take the derivative of n squared over n cubed plus 1, see I'll have 2n times n cubed plus 1 minus the derivative of the denominator will be 3n squared times n squared in the numerator, all over n cubed plus 1 squared. And this kind of simplifies a tiny bit, so let's see, we would get 2n to the 4th minus 3n to the 4th. So I would have 2n minus n to the 4th in the numerator over n cubed plus 1 squared in the denominator. Now notice that this will be negative for n, well, as long as the numerator is negative. So as long as n to the 4th is greater than 2n, which means that n cubed is greater than 2, which means that n is greater than the cube root of 2. Okay, so that's good. That shows that eventually it'll be decreasing. So this shows that it's eventually decreasing. And that's really all we need here, is that it's eventually going to be decreasing. And the second condition that we need to show is that the limit as n goes to infinity of the terms in absolute value, n squared over n cubed plus 1 is equal to 0. In this case, it's easy to show if I divide out the n cubed. Divide n cubed, and then divide the n cubed here. We get 1 over n, and then we get 1 plus 1 over n cubed. And then all this stuff goes to 0. So I'm left with 0 over 1 plus 0, so 0. Okay, so we showed it's decreasing and that the limit goes to 0, and therefore is convergent by the alternating series test.